Aluminium-based nanocomposites. I will start with like exactly what we do. I will give some slides and who are the people behind all the innovations what we are doing here. So as Madam already said that I'm from NIT Raipur. AMC is Advanced Metal Casting Laboratory, which we have established in 2017, and thereafter we are progressing with a very good space. Now, these things already, Madam has already said about me that I have some amount of international exposure in different areas. However, my area of interest is more on metal casting and solidification. Uh, I have to first thank my students who are basically the major force behind whatever we do. So we always have some postdoc students. Till date, we had three postdoc students, where two of the postdoc students were my PhD students itself. Later, they joined as postdoc, and then they got job. Uh, Presently, I have two PhD students. We don't have any master's degree in NIT Raipur in metallurgical engineering. However, we do have PhD and undergrad students. So there are a lot of undergraduate students who starts working from their second year. And also a lot of students come from other institute in summer internship. And I would like to thank those students also who have helped to develop our technologies and all. Uh, about our funders and collaborators, it's very important because without funding, you cannot do research. So our major funding is coming from industry. So as I am working on aluminium, so Vedanta is one of the biggest funder of our projects. So far, we have got near about 50 lakhs of funding from Vedanta itself. Balco has started funding. We are in discussion with Hindalco, which is an Aditya Birla company, and they are also interested to fund some of our ideas. Ziomax is a company. It's a UK-based company. We have a collaborative research funding from them, and we have applied for Indo-UK collaboration. Coldforge is a automotive company which is basically in Faridabad, and they make automobile parts, and they have also funded some of our projects. Now, from government projects from India, we have SCRB DST funding, and Royal Academy of Engineering is a UK-based funding, UK government funding. So they have also funded near about £50,000, which is around about 45 lakhs. And about institute collaboration, most of our collaboration are with company institutes abroad. So Warwick Manufacturing Group, WMG, it's the world best manufacturing group situated in Warwick. And we had one collaborative research program with them. Tom State University is a Russian university. At present, we are in a negotiation level with them for certain Indo-Russia funding. Brunel University, I have already worked there for 3 years, and presently we are collaborating with them. And UACJ is a Mexican university, and we don't have research collaboration with them. However, we do have some academic collaboration. Some of the lectures from of their university, and they also give some lectures here. So it's completely academic. About Raulkela, we have some joint research funding with NIT Raulkela, and also we are also looking for other IITs like IIT Kanpur. We have some joint collaboration we are starting, and other IITs or any other colleges who are interested to collaborate with us. Now, this near about 1.5 crores funding we have till that in last 7 years, and the red ones we have already finished, and the black dark ones are basically running projects which are going on. Now let us come to the problem statement, like why we are doing the research part. So in this graph, you can see that the number of vehicle is growing day by day, and it is going to almost double or triple in near 2050 or something like that. Now that is a huge problem for a lot of us, because they will emit a lot of scrap, they will emit a lot of CO2 emissions. So we have to start thinking about these things right now, so that we don't face problems later. So these are the numbers of like vehicles, how many vehicles will be there. So 1450 million vehicles will be on road by 2030, and they will consume near about 2000 billions of oil. So, and also a lot of CO2 emissions will be there, and a lot of vehicles will be scrapped, because in India generally you can sell the second hand cars or third hand cars, but most of the other countries, the developed countries, they do scrap their products. So we have to start thinking on all those things. This is a cartoon to show that, like, if you get 150 million scrap cars, and if you stack one over another, so you may reach moon by that. So that shows that what number of scraps we will develop in near future. Now, when the technology has advanced, we have seen that the weight of the car is increasing day by day. The reason for that is basically the safety issue. Earlier, when initially the motor cars were there, it were very light, and but the speed was not that great. So what happened? The accidents were not that fatal. So when you are increasing the speed, then your car should be crash resistant, and if you want to make it crash resistant, people use more metal on it. So that basically increases the weight of the car. Now if there is a increase in the weight of the car, definitely it will consume more fuel, and then it will emit more CO2 gases. So that is the issue which we are basically addressing. Now, this is the mechanical student can easily understand that if the weight of the car is high, then definitely there are a lot of things will act on it. Acceleration resistance, the weight works there also. If you accelerate the car, rolling resistance, if you are going uphill, so sorry, gradient resistance is there, rolling resistance is there. Only aerodynamic resistance is depends on the design of it, but the rest of the things are basically directly affecting the weight of the car. Now if the weight is increased, then the CO2 is increased. Now here we can see that how much amount of CO2 will increase when we are increasing the weight. And increasing CO2 means basically you are spoiling our atmosphere. So what people are doing, they are trying to use aluminium alloys. In aerospace or aircraft, aluminium is vastly used, because the price is not an issue. So the quality and durability and accident resistance is very important in aeroplanes. So you can use aluminium, but the same thing when you are going for the car, the price of the car will increase. But some of the companies are basically using more aluminium extruded products in the cars. So this is two cars comparison. You can see one is a sedan car and one is a mini car. The sedan car is basically JLR. JLR means Jaguar Land Rover, which Tata has already acquired it. You can see that an aluminium frame of JLR sedan car is equivalent to the weight of BMW mini car. So that means that this big car and will spread same amount of CO2 emission as BMW mini. So that is how, when you change the material, uh, then you can get better output. So these are some of the factory images of a Range Rover. You can see the car structure is being made by your aluminium alloys, and these are so light that two people can lift this kind of structure. There's some more pictures of aluminium frame cars you can see of Range Rover. Now, why I am talking about cars only? Because there are a lot of modes of transport. This rail is there, aviation is there, ship is there. But if you see the pie diagram, then the 41% of the cars basically uh, are there in the transportation, which contributes to greenhouse gas emission. Okay, so that is the real concern. Now, we are aiming to drop down the weight of the car so that the direct CO2 emission reduces. Now, for that, what we have to do, number one, you use the lightweight material. The lighter weight is aluminum, more lighter is magnesium. Okay, or you can or why we are using aluminum and magnesium? Because their density is very low compared to your steel. So aluminum has one third of the density of the steel, and magnesium has one fourth the density of the steel. However, the strength and cost of production is the issue here, because steel strength is very high. So it is very difficult to replace steel. If somebody says that I can replace the steel, so it will be really an engineering challenge. And also the cost of production, because aluminum production cost is much higher than the steel production cost. And a lot of other factors like recycling and other things also comes into play when you are talking about using the lightweight materials. Now, what else can be done by this? So, in this figure, you can see that we start from Mother Earth, we do mining, we get the raw materials, then we extract the metals out of it, and then we get the bulk metals and we process it to engineering materials. And when we design and then we manufacture various transportation products. And after the performance service is over, then the life of that components ends, and basically we dispose it again. It's like in recycle, we don't go for recycling, it is dumped in dump yards. But in India, mostly we basically reuse. If it is not working, we will fix it and then again we reuse. Sometimes we remanufacture it. Okay, but this has to be there, like to minimize the energy consumption. We have to reuse, remanufacture, recycle, and do recovery whatever we can get, so that we don't dump the things and the cost of production is decreases. Now, as if mechanical engineers, what they can do, they can design the structures such that the weight less material is required, and that can be easily recycled. It can be easily detached and recycled. As a metallurgist, what we can do, we can basically refine the structure or use certain alloys, composites, so that you can get the better mechanical properties with lower weight. Okay, and another thing also we have to do is we have to check our processes, the present processes. Can we come with some new processes where the cost of production decreases? So these are the things we can do to solve the problem. So I have listed these challenges and what exactly we can do. So let us discuss with aluminum and its alloys and its composites. So how we can strengthen it? Either you can do alloying, or you can reinforce it with certain particle, improve the strength, hardness, wear resistance and all, or you can refine the grain structure and you can improve the strength of it. Now, let us go with number one is alloy. Alloy, okay, we have almost tried every combination. Some people are still working on alloy development, but still most of the combination has been tried. But most of the alloying processes are basically batch type of processes, which is uneconomical. So we can try to make these batch processes into continuous processes, alloy making process. And then the thing is, by deformation and homogenization, basically, like deformation homogenization means you are doing rolling, then you are doing heat treatment, then you are doing cold rolling, heat treatment cycles, this kind of stuff. By that also you can improve the material property. Okay, but if you are doing that, then you have to give lot of capital investment. Then the running cost will be very high, because if you are putting a rolling mill, it will be a half-kilometer long rolling mill. So a lot of rollers will be there. Running cost will be very high. High energy consumption will be there, because more electricity will be used. And because all these processes are going on, so a lot of greenhouse gas emission will be there. So can we develop certain technologies where we can basically homogenize the cast product and get a near net shape product, so that we don't need to have a huge rolling mills or continuous processes like that. About grain refiner, there are certain processes like problems like fading and segregation, uh, where the grain refiner basically doesn't work. And the segregation is like, if the refiner is basically segregated in when you are casting, so it doesn't work, it doesn't refine the structure. So we have to think whether, first of all, no fading should be there and there should not be any segregation. That is number one. Number two, it will be more better that grain refiners itself is not required, because making grain refiner is also a extra process and it is a money consuming process. So, and grain refiners are nothing but again a composite type of stuff. So that also we have to look at. Now about metal matrix composites, if you see that most of the metal matrix composites are made by your batch type of process, and anything done by the batch type of processes is basically expensive. And if you are adding any micron level reinforcement in any composite and you do tensile testing, your material prematurely fails. You never achieve more strength than the base metal. That is because there will be always a cast defect inside the MMC. Now you have to get rid of these cast defects. If you can't, then your material will have premature failure. And the toughest part is reinforcing nano particles inside it, because nanoparticles tends to agglomerate. And again, this is also a batch type of process to people who are working on nano reinforced composites. So what we can do is, first of all, make all the batch process to continuous process, eliminate the cast defects, then bulk production of the cost effective nano reinforced. We have to produce in bulk so that the cost of the nano reinforced composite goes down. So that should be our probable solution. Now, based on this table, let us go for further understanding by the pictures. Now, I told you batch type of process. Now, this is an image of a furnace where we basically make alloy in industries. So what happens, suppose this is 100 ton of liquid metal is there. Now, if you get an order that you have to make only 20 tons, now you have to use the same furnace. Now that is an issue, that then again the full furnace will work in capacity. And if you buy smaller furnace, then if the order comes for 500 tons, then you have to buy a lot of furnaces. So the thing is, for optimizing the processes, we cannot think about just the batch type of process. And sometimes, suppose you have to cast 100 tons and you will sell 50 tons, and 50 tons is now you are waiting that next customer will come, right? So those are some of the issues of the industries. Now, about making metal matrix composite, most of the metal matrix by liquid metallurgy route is done by stir casting process. What you do, you take a mold, you have the liquid metal, you stir the liquid metal, you get a vortex, you add the particles in the vortex, and then it get mixed. But again, this is again a batch type of process. It is not a continuous type of process. So if we make it a continuous type of process, then the production will be high and the cost will immediately decrease. So how we can do that? About grain refiner, I have told you, grain refiners are basically the rods, and they have titanium boride in aluminium. It's like a composite itself. This titanium borides acts as a nucleating site when the solidification is occurring, and you will get the fine grain structure like that. So the industries, they buy these grain refiner from European countries, and then it's very costly, and then they use it for refining the grain structure. And what are the problems? Already I have told you about the grain refiners. Now, what is the beauty of the grain refiner? When you have added the grain refiner, if you can see A and B, these are basically without grain refiner. You can see the bigger grain structure. Okay, and this process is basically TP1 test process. I will show you some of the schematic later, where we basically measure the grain size of any metal. So you can see the bigger grains, and when you add grain refiner, you will see the fine grain structure. And there is an equation called Hall-Page equation. The metallurgist may know, it's very familiar. If the grain size decreases, the strength increases, irrespective of your chemical composition or alloying or anything. Okay, so that is the beauty of grain refiner. Now, how it works? Suppose TiB2 is a particle, nanoparticle, you are putting inside the liquid metal. It will help in nucleation of a grain. These are the TEM images, and you can see that aluminium is nucleating on TiB2 surface. Okay, so if you have lot of particles inside the liquid and the solidification starts, then each TiB2 particle will start nucleating, and you will get lot of fine grains, and these grains will stop the grain growth of the other grains. So like that, you get the refined structure. Now, let us come to some basics to understand what exactly solidification is. So, solidification is basically transformation of a liquid into solid. That is the simplest thing we can understand. And how it happens, number one is the nucleation, and number two is the growth. First, there will be a nucleation. So, nucleation is a separate science, and growth is a separate science. Now, nucleation can be further categorized into homogeneous nucleation and heterogeneous nucleation. So, two types of nucleation. What is homogeneous nucleation? In liquid, the atoms will come together when the temperature drops, and they will form a cluster. So initially one cluster will form, but there will be again latent heat release. So this cluster will again break up. As next you are dropping the temperature, more atoms are coming closer, making a bigger cluster. And when a nucleus is formed, a critical diameter is formed, then the growth starts. Okay. But in heterogeneous nucleation, there is always a surface, and on that surface, the atoms from the liquid is coming and sitting, and then slowly growing. Now, heterogeneous nucleation always takes place because it is very easy to happen. Homogeneous nucleation is very difficult. And first of all, if you are casting something, you are putting inside a mold, right? So there is already a mold wall, and from where the heat is being extracted. So already you are giving a surface. So heterogeneous nucleation will always takes place. So homogeneous nucleations never takes place practically, but in lab scale you can do homogeneous nucleation. But in homogeneous nucleation, again, you have to drop the temperature further, much below than the melting point to achieve that. Okay. Now, about the structure, I have shown you some microstructure of EQX structure. Now, how different type of structures are formed: faceted structure, columnar, dendritic structure, EQX structure. Okay, so some of mechanical students also know that how the structure happens in the surface, and then the columnar structure and EQX structure at the center. In the normal textbooks you can see, but these structures all depends on what is happening inside the liquid metal in front of the solid, which is solidifying. And it also depends on the temperature gradient. Temperature gradient means what is the temperature at the center and what is the temperature at the surface. If the temperature at the center is very high and the surface is very low, so maybe faceted structure will happen. You can see the red line. So slowly from the red line, it from vertical, it is going to horizontal shape. So if it goes down like this, then different type of these kind of structures will form. Okay, and irrespective of adding any grain refiner or alloying element, you can change the structure by changing this type of thermal gradient and the situation inside the liquid metal. Now, about the segregation, I have told you you may have heard about phase diagram. Metallurgist may know it is a very simple thing. But whenever a solid solidifies, the solubility of that solid, like suppose this is basically a phase diagram. So you have temperature in your y-axis, and x-axis it is a composition, right? So here it is liquid, then liquid plus solid and solid. So you are taking a composition. The red line is the composition. So from the liquid, if you go down and if you touch this part, which is basically called liquidus. So if you want to check what is the percentage of solute in it, you have to take a tie line, and when it touches the solid, and you have to take this is CS1. Now if you see that CS1 is less than CO. Okay, so initial composition you are targeting, suppose 4.5 something, you are getting something 1.1%, something like that in CS1. So rest of the solute is now dragged towards the liquid. So this diagram, you can see that the solid is growing and it is pushing all the solute in the interfacial region, and this is unavoidable. Okay, you may have fine grain structure also, but you will have this segregation around it, so you cannot eliminate it. The only thing you can do it, if you have big columnar grains, all the solutes will come to the center. Suppose the columnar grains are like this, all the solutes will come to the center of the casting. Now, if you have this kind of segregation, it is called macro segregation. Macro segregations are very difficult to get rid of. So you have to do a lot of homogenization treatment to get rid of this, and that will consume a lot of energy. And suppose your solute density is quite high, so it will tend to go down by the gravity. Now that is another issue with it. I will show you some aluminum tin experiments also later. So these are some of the issues which have to take care of when we are working on it. Okay, so I've talked about force convection. This is a force convection technology where we basically change the solidification mechanism. What solidification happens, like nucleation, the growth part, those things we can change by this technology. So the first one is basically the twin screw machine. Okay, so what these machines are basically doing, it is creating a convection uh, when the solidification is happening. Okay, and whatever theory we have, we basically assume that there is no convection, and based on that we have these theories of nucleation and growth. But here we are trying that what if we introduce more forced convection, what happens to the solidification. Now in this twin screw machine, basically you feed the liquid metal, your composite material, whatever you want to add from the feeder, and it will go like this. Two screws are rotating clockwise, anti-clockwise, and there will be a lot of convection going in this chamber, and finally you will get the composite or the alloy or whatever you are adding in it. Now problem with this is, suppose what material you will use to make these screws, because you cannot make it by the ceramic, because ceramic may break, because lot of loading will be there when they are rotating. Number two is you cannot make with the metal, because most of the metal are soluble in other metals. So it is a very critical thing. So that's why this was not very much taken by the researchers. The second one, this one is basically a rotor device where a rotor is there and there is a stator. So rotor rotates and there is a stator and there are some small holes. I will explain the mechanism later, because we are using this rotor stator device. This rotor stator device is much easier and less complex than this twin screw. So twin screw and rotor stator device are basically like mechanical means of force convection. Then we come to the third one below here. This is by the electromagnetic. By electromagnetic forces, by Lorentz forces, you can stir the liquid metal. So this is very good one, because here there is no contact with the electromagnet and the liquid metal. The electromagnet can be outside the mold, right? And then by that, the electromagnetic field will penetrate in and it will stir the liquid metal. The fourth one is basically your ultrasonic way of creating the force convection. So there is a process called cavitation process. So you initiate, when you pass ultrasonic sound, then there will be formation of very small voids. Then these voids will capture a lot of dissolved air inside it. It will increase, and when the pressure of these when these voids are increasing, the bubbles are increasing, the pressure inside will go less and there will be a collapse. And when it collapses or implodes, then there will be a lot of agitation inside the metal, and by that agitation you can create a convection inside the liquid metal. Now what we have done with all this information I have shown you, so we have made a DC caster. DC caster is a machine which is being used by aluminum industries, where there is a mold which is basically top and bottom open. So you put the liquid metal there, you have a stopper plug. Initially the stopper plug is here, so you fill the liquid metal, and when the solidification starts, you draw down this stopper in the bottom, and you slide it with the help of pneumatic or electric or hydraulic system. And what happens, the liquid converts into solid directly. So what happens that a very small mold can cast huge length of billets, ingots, like that. Now this is a rotor-stator device. We have placed a rotor-stator device which I have shown you earlier. So we are creating a forced convection when the solidification is starting. So we want to see that what exactly will happen when create an extra force convection when the solidification is taking place. So we designed a full machine here, which is a lab scale DC casting simulator. And in this you can see the hydraulic system, and you have the billet casting stuff. There are two furnaces there in the design. And this is the picture where we have manufactured this in our laboratory. Everything was manufactured by our students. We have indigenously developed, designed this process, and we have done all the experiments. Nothing was like, only the furnaces were purchased, and rest of everything was made by us indigenously. Now you can see the video how it works. So you are pouring the liquid metal. You are using the rotor stator device now at the top, and the casting has started. You can see the piston now, piston going down, and the billet coming out from the bottom. So this is how the microstructure changes. Now let us show you the macrostructure. So if there is no rotor-stator device, you get big columnar grains, random grains. Center there are fine grains, side there are fine grains, then at the middle you have the columnar grains. When you start forced convection, all the structure changes into fine grain structure, and for alloys it is more finer. So this is the beauty, by without using any grain refiner, by just introducing a forced convection, you can change the structure. Now what is it basically says, that you are decreasing the grain size, and by decreasing the grain size you are increasing the strength of the material without changing the chemical composition. Now again, we have added tin. Suppose we are adding a heavy metal. The tin is very heavy, density of the tin is much higher than aluminium. So if you don't use a rotor stator device, then the tin will settle at the bottom. But if you use it, it equally distributes inside the billet. So you can beat the gravity, you can beat the columnar grain formation by the forced convection machine. We have a patent for this technology. And next one is basically by the electromagnetic one. Now earlier one was by the mechanical force convection. This is the electromagnetic. I have shown some photograph of TP1 test procedure where we basically measure the grain size. So this is basically a equipment which is a TP1 test. So this is the mold of TP1. It is basically a conical type of mold where you pour the liquid metal and you place it here, and the water jet comes from the bottom. And when the water jet comes, what happens? The solidification starts from the bottom to the top, and you will get more columnar grains from the bottom to the top. Now, if you have good refinement, then these columnar grains will not form and you will get a refined structure. So that basically shows how good your grain refiner is. Now, we are not adding any grain refiner. Our motive is to create a forced convection. So what we have done, we have put one electromagnet around it. Okay. And we wanted to see that what exactly happens. Can the electromagnet, rotates the liquid metal or not? Now I will show you the video. You can see it carefully that how the electromagnet works. So the same thing, same design. And this is also made indigenously in our laboratory. You can see the electromagnets. The student is switching on and off. You can see the motion of the liquid. You can rotate the liquid. Clockwise, anti-clockwise, both direction you can rotate by changing the current. Now it is solidifying. You can see slowly the motion is now decreasing. So now without adding a mechanical stirrer also by electromagnets, you can basically rotate and have a forced convection. So based on this result, let us see what we get. Microstructure. So again, we take the section of it, and the top section, you see there is certain amount of refinement. Now if we quantify it, we see that the grain size decreases with the current. Now current means what, if you give higher current, you get more magnetic field, right? So when you are seeing, you are adding increasing the current, the grain size is decreasing. Now this is the beauty of it. Like, it is not like how much amount of grain refiner now you have to have. It is about how much current you are giving to the liquid metal during solidification, and it will create the magnetic field, the stirring effect, and finally decrease the grain size. So we are completely eliminating the presence of grain refiner here. Now that is a test procedure. Now we have to see whether this really works in real industrial scale, or in some prototype or not. So we made a twin roll caster. Now what is twin roll caster? Twin roll caster, we do have two rolls rolling in opposite direction. You put the liquid metal from one side and you get the solid strip. Now you can make near net shape strips, so you can eliminate all this hot rolling, cold rolling process. You cannot eliminate, but you can certainly decrease a lot of hot rolling stuff and cold rolling stuff by this, and you can really save a lot of running cost and capital investment. So this is the twin roll caster which we have designed and manufactured in our lab, and we have put some electromagnetic stuff in this twin roll caster when we are putting the liquid metal. Now let me show you the design, our design. So here there are two rolls inside this. These are the roller assembly, and these are internally water cooled rolls. So here you can see that there are some grooves on the rolls inside. So the water runs in these grooves, and there is a sleeve at the top, and it is water cooled. So the temperature is completely maintained in here, right? And then you have the tundish here from where you will put the liquid metal, and the magnetic field is there which will rotate the liquid metal during the solidification process. We have also patented this technology. This is the picture of the real one. So here, this is the magnetic field we are generating. This is the tundish. We will pour the liquid metal. There will be some turbulence here, and then you will get the sheet metal casting. So these are some of the castings we have tried with the different pouring temperature, different current, and we tried to understand that which is giving you the better casting. So in lab scale, we do extreme experiments. So you will see a lot of strips are very ugly. So we are doing some extreme stuffs, and then we are getting some good quality also from those combinations. Now this is the sectional picture. Like if there is a strip, so you cut the strip and you take the cross section. Now cross section we have seen under Polaroid optical microscope to observe the grain size. So normal twin roll casting will give you bigger grains, random, fine, big combination of these grains. But when you put this electromagnetic stuff, you get the fine grain structure all over it, right? So that is the beauty of the technology. Now here you can see the grain size distribution, the previous picture. You will see TRC is the black one. You will see that the grains are basically increasing, decreasing, and a lot of randomness is there. Even the standard deviation is very high. But if you see the forced convection one, it is quite uniform from one surface to another surface. So we can achieve a uniform grain structure. If you see the elemental composition, there is a lot of segregation in the case of twin roll casting at the center, but it is quite uniform for the normal twin roll, for the forced convection twin roll casting. Now about homogenization. So we try to do some homogenization of these stuffs. After 3 hours of homogenization, we still find some bigger grains in the twin roll casting stuff. But after just 1 hour, you get very fine equiax structure in the case of forced convection twin roll casting. In the next one, this is the complete cycle of how you are basically homogenizing these strips. And you will see that for TRC, it is very random, very big grains. But for forced convection, you after 15 minutes, you can get very equiax, fine grain structure, and it stays constant, right? Now the thing is why this happens. So we came with a theory of solidification, what exactly happens. So these are basically two rolls which are rotating, uh, and the liquid metal, the yellow part is the liquid metal, and these are the solid which is growing from the surface. So if the solid, there is no convection, the solid will grow from the surface to the interior. And when it happens, whatever you are adding inside it, any composite material or any alloying elements, everything will come at the center of the casting. Now, when it comes to the center of the casting, it drops down the melting point of that. That is understandable by the phase diagram. And what happens that your twin roll casting is divided into two parts. Actually, it's just not a casting, it's casting as well as rolling. So it has a casting part and a deformation part. So when it passes, this happens, the deformation region basically decreases. And when the deformation region decreases, then what will happen? There will be no deformation and no dynamic recrystallization will happen here. But if you have some convection, if you are adding any particle, or if there is any alloy, the nucleation starts in the liquid, not from the surface to the interior. And your deformation region basically increases. And when the deformation region increases, you increase lot of defects like dislocation and all, which helps in recrystallization, dynamic recrystallization. So it is very easy when you have more deformation, and that's why less time is required when you are heat treating the material and getting the structure. Okay, now let us come. This was all about what kind of things we are do. Now I am going to the nano composite part. Uh, Now nanocomposite is basically made by a lot of processes. So one by one, I will tell you the different processes. Number one is your powder metallurgy process. This is very easy process to do. You take the different powders, you mix it, and then you do compaction, and you use different type of tools to get different shapes, and then you do the sintering part. Now, during sintering, you make the composite or the components. But the problem is when you are adding all these particles and all, you are not able to take out the air entrapment which is already there. So there will be certain amount of porosity left in this kind of process. Another thing is you cannot make very huge production by the powder metallurgy route. You can make a lot of products, small products, but huge products are very difficult to do because you require a lot of hydrostatic pressure. Next is basically the equichannel annular pressing. Here what you do is you are basically mixing these materials in a L type of pattern, and then you use a plunger and you are forcefully bending it, and you are thinking that it's going to mix. But it's very difficult because it's a solid stuff process, solid stage process, and it's very difficult to get a uniform mixing of these particles. Now, the third one is your accumulated roll bonding. So you take the particle, make a sandwich, and then you start rolling it to thinner section, and you assume that there will be a nice mixing. But I doubt, because these particles will stay at the middle, and it will make a sandwich type of structure, but it's not going to uniformly give the uh, distribute the nanoparticles. The next one is basically high pressure torsion. So you make first those tablets at the center and create a torsion force so that it mix or it joins together to form. Again, the limitation, like powder metallurgy route, there may be porosity and the size restriction is there. Then friction stir process. Now, basically, this is used for welding process, but some people have tried by adding particles when you are doing the friction stir. But again, it will be on a line joining part. But how you are going to make a plate out of it or something, a bulk material out of it, is a challenging stuff. The second last one is ultrasonication. Ultrasonication is widely used by a lot of people to make your nano composites, but ultrasonic forces basically doesn't incorporate the particles inside the liquid metal. What it does is basically it uniformly mixes it, but you have to incorporate it by the stir casting process, and then you will use the ultrasonic process to uniformly distribute these nanoparticles inside the metal. So ultimately you have to do the stir casting process. So initially I showed you there will be a vortex formation. In that vortex you have to add the particles. Now when there is a vortex formation, what happens, the anything in the surface goes inside the liquid metal. Now suppose you form some dross at the top, some slag is in the top, or air is in the top, everything is going inside your liquid metal, so it will be full of porosity, gas bubbles, slag, or whatever unwanted thing was there in the top is going inside, and finally it is contaminating your melt. And now you are doing casting and do whatever ultrasonic treatment and all, you are not able to get rid of those things which you have added by creating the vortex. That's why we went for the rotor stator device. So earlier I have shown the picture of rotor stator device. Now I will show you the video so that you can understand that how exactly this rotor stator works. Now there are suppose particles at the bottom of the liquid. Now when the rotor rotates, these particles will be sucked from the bottom, and from these splash holes in the stator it will throw the particles inside the liquid metal, and it will give a very good mixing. And the beauty of this stuff is there is no vortex formation at the top, so whatever is in the top doesn't come inside it, so it is not contaminating. But the only problem is it is sucking everything from the bottom, so you have to feed your particles from the bottom, and that is a challenge ki how you are going to feed that particle from the bottom. So these challenges we have accepted, and then we came up with this design. Now what is this design? This design is basically we have a mixing chamber, we have the rotor stator device. Now instead of pouring the liquid metal from the top, we are pouring from the side, and it is going below this chamber and coming out from this baffle, and then it is hitting the rotor stator device, and then it is started mixing. Now when rotor stator works, there is no vortex formation at the top, so any contamination at the top is not coming in, and you are getting the liquid metal from the top. So this is the idea we came out with, and we made a insulation stuff because all the liquid metal stuff will go there, so we have completely insulated it with heaters and all, so the metal stays in the liquid conditions. I will show you some videos that will clear the idea about it. So first I am showing you the water model. So in water model you will understand that what exactly happens. So here what we are doing, we are with a pipe, we are putting the water in it. Now you see the water is there. Now we have dropped a particle. This is a graphite, a chunk of graphite we have thrown inside the pouring chamber. And what happens when it hits? It hits and it mixes. So it is going through that baffle, it is going to hit the rotor stator device because it is sucking from the bottom, and it mixes very uniformly and it goes out. And when you see the video from the starting, there is no vortex formation at the top. So any particle you add, it is going to mix very nicely. And when you are doing it, you can see it is a continuous process. You don't need to do batch type of, you can add the part as much as particle, as much as liquid metal in it, and you can do it. Now the same thing I will show you with which we have done with the liquid metal process. This is also in laboratory. So this is my PhD student Sandeep Biswas. Presently is like a faculty member in OPJU, he's holding the crucible. We have liquid aluminium there. Melting temperature is near about, sorry, the pouring temperature is near about 950 degrees centigrade. It's pretty hot. Uh, all these tongs and everything we have designed as per our requirement. The other students are undergrad students who are working on it. So when we do this experiment, first of all, when you take out any liquid metal, you have to take the dross out, because there will be a dross which is forming on the surface, which is basically aluminium oxide or any other impurity which will float at the top. So basically we remove that from the top surface. Now we have almost clean liquid metal. In industry you can also do degassing. So we are not doing degassing because this is a lab scale experiment and we wanted to validate. Now in water model, like we have poured the water, now we are pouring liquid metal instead of the water, and by hand the students are adding these pellets, which are basically can be a master alloy, it can be a grain refiner, it can be a composite material where you have higher amount of particles in it, which will mix inside the liquid metal. Now when it goes, you will see it, this is the rotostator device stirring, and the composite material or the alloy or whatever you are adding, the mixture is coming from the top. So what you have seen in the water model, you can see the real stuff here in this video. Okay, so let us go to the next one. So these are some of the microstructures which we have obtained. So the first three microstructures are the composites. These are macro level particles first we added, and these are the grain refiners. TiB2 we have added inside it, and you can see the amount of refinement. And then aluminium copper alloy, like you are adding aluminium copper master alloy, and if you change the feed rate, by changing the feed rate you can basically design the alloy. So if you want more copper, you increase the feed rate. So by controlling the feed rate, you can basically get the different compositions. And the beauty is you don't need to stop. You can continuously do this by this continuous process. You can change the alloy, you can change the percentage of grain refiner, you can change the amount of particles addition in it. So we have the patent for this process also, and a lot of publications are also there which you can follow. Now let us come to the nanoparticles. So why we will make nanocomposites? So that was one of the things. So our industrial partners, they were looking for electrical applications. So basically the electrical wires are, earlier copper wires were used, at present aluminium wires are used. Aluminium has poor conductivity than copper, but it solves the purpose because it's much cheaper, but the strength of aluminium wire is not that great. So can we increase the strength without decreasing the electrical conductivity? So initially we attempted with graphene, but the pure graphene was not available in the market, so we went with GNPs, graphite nanoplatelets, and they also have very good conductivity. And we have just modified our continuous caster with a wheel shaped stuff, where the mixing will be there, and you will get a formation of the rod which will contain it, and then we will do the rest of the studies of conductivity, strength and all. Now these are the various parameters we have used in this process. I'm not going through the details. We have obviously patent of this design also published in Journal of Manufacturing Processes, so you can refer to this paper also. We have also got one DST project based on this. Now suppose nanoparticle has gone in. Now how you will confirm that whether the nanoparticle has gone in? because macro you can see by optical microscope or scanning electron microscope, but you cannot see the nanoparticles. And we don't have transmission electron microscopy facility. So initially, to understand that, we went with a very smart idea that let us dissolve the aluminium in sodium hydroxide solution. Aluminium will react, it will dissolve, but the carbon will not. So we took water, we add 10 grams of sodium hydroxide in it, we got the solution, we added our composite material. So what happened? Aluminium was in the solution, and the liquid turned into black color, and then we filtered it. Now it is black color, but whether it is carbon or not, so we have to do x-ray. So we did XRD, we did EDAX, and we found that yes, these are basically GNPs. So this is a initial understanding that yes, the nanoparticles has gone in, means very cheap way to understand. But again, there will be a question that the particles may go in, but maybe they are not uniformly distributed, maybe they are agglomerated. So how we are going to understand that? So for that we went for transmission electron microscopy. Now, before that we did some SEM, and we took some dot mapping. We found that if you see the carbon, see lot of dots uniformly distributed. Okay, now the problem with EDAX is it will give you that yeah, carbon is there, but whether this carbon is that GNP carbon or not, that confirmation it is not giving. But it is showing that there is certain distribution of carbon around the matrix. Now this is TEM. Now the people can say that yeah, you have taken TEM, so maybe the particles are there only, it is not uniformly distributed. That could be a question. So what we did, we didn't do a lot of TEM, we just did 2 TEM samples, a big billet, and we did only 2 samples, very small samples. And if it is uniformly distributed, we assume if it is uniformly distributed, from that 2 samples we will get the GNPs, and we found it for both the samples. So that means GNP has uniformly distributed. So if it is not uniformly distributed, if we take 2 samples, it is not possible to get GNP on those samples. So by that we can assume, or we can confirm also, that we have uniformly distributed these particles. And these nanoparticles can only be done by this rotor stator device. If somebody is selling you a normal stirrer, it is very difficult or impossible to incorporate nanoparticles in any liquid metal. Now let us see how the properties work. So we took initially we are having these rods. Now from one end to the another end, yeah, or the cross section, we are taking the cross section, and diameter wise we are taking hardness of it. So for various samples, so 0 means pure metal, no this thing, we saw some higher hardness at the center, and same thing is happening to all these composite material, nanocomposite. At the center, the hardness is increasing. Now for alloy system, what happens? The solute is basically rejected towards the center, and when the solute is rejected to the center, it increases the hardness at the center. Now same thing is happening with the nanoparticles also. So you are uniformly distributing it, but some amount of GNPs will be pushed because their size is very less. So the solidification front is basically pushing those GNPs, not all, but some amount of GNPs to the center, and which is basically increasing the hardness at the center. Now also we have checked the porosity. Now when we see the porosity, we find that in the composite, the porosity is relatively higher compared to the alloy. Now I have told you that there is no vortex formation, nothing can go from the top, no air entrapment is possible, but still there is some percentage, 2.5% in casting is not that much for composite, but still it is some amount is there. Now that is because when we are making the pellets of these nanocomposites, from there we are not able to get rid of the porosity. Now those porosities are basically contributing in the final casting. So now presently you are working that how we are going to add these nanoparticles inside it without having enough porosity in it. Some of the mechanical properties you can see. Now this is the beauty. You have the tensile graph of the alloy, and you see all the composites are having higher strength. If you do with macro particles in it, the strength is never going to go high. It will have premature failure. Here there is premature failure. You can see the graph elongation is not high. It is failing when it is rising for all the composites. But the strength is definitely increasing. So that means it is contributing, it is resisting the motion of your deformation. And if you see when you are increasing the percentage of these nanoparticles, the strength is decreasing. And that is quite surprising. It should increase, but it is decreasing. So we thought it is attributed to the porosity one, because when you are increasing the particle, more porosity is there. Porosity will help in premature failure of the material. So we have repeated this, and more or less we got this kind of stuff. And the next one is the yield strength and ultimate tensile strength of both of this, which I have already explained. This is the Young's modulus. Young's modulus is more in the composite. Definitely the stiffness will increase when you are adding this particle in it. And in the earlier figure, you have seen that elongation has decreased for the composite materials. Now let us see the mechanical properties, where the fracture surface analysis we have done. So we have done all the fracture surface analysis. Most of them shows cleavages, very few amount of dimples, some cracks are formed. So it is, as you have seen, that we don't have much elongation there. So the dimples are less, ductile failure is less, you are having more brittle type of failure. This can be further improved if we do some amount of working on it, or some amount of heat treatment on it. We can get rid of it and we can improve the ductility. So those things we are in process to develop or to improve by other mechanical means. We are trying to do it. Now, when you are doing any fracture surface analysis, don't always see the fracture surface. You always check what is beneath that fracture surface. So we take a section of the fracture surface and we see what is going on there. So we saw a lot of elongated grains for all the composites. That means there are some amount of elongation is there. That means that nanoparticles are not resisting the elongation. Means it is allowing the material to elongate. However, they are basically failing. And that was again interesting. We measured the grain size of those elongated grains. Now what we are seeing is that with increase in the nanoparticles, the grain size is decreasing. So if the grain size is decreasing, that means these particles are doing something. GNPs are not a good heterogeneous nucleating site, that it will create lot of nucleating sites like titanium boride. Earlier I have shown you, but it could be working as a pinning agent. Suppose one grain is trying to elongate, grow, then these are not aligned to grow. So that is one of the possibilities of that. Other than tensile testing, we did again compressive testing, and these are the compressive test results. And in the compressive test results, we didn't find that UTS is much better than your tensile strength. It is either same or it is dropping. You can see the Young's modulus has dropped, means it is not showing that stiffness. In compressive load, it is just showing something different. So this is very interesting for us, and we are trying to understand this, what why exactly it happens. But we understood one thing, that if you are making nanomaterials, it will give you good tensile strength, but compressive strength you should go for macro level, sorry, micro level reinforcement, not nano level. So these are again the sectional stuff. Here also you will get elongated. Those were vertical elongated. This is horizontal elongated grains, and deformation is occurring in the both the shapes. We did some modeling. The modeling part is basically done by my students. Most of my students are mechanical engineers. I am not very good and expert in modeling stuff. So they try to understand that why this grain size is basically decreasing. And to understand that, they did the modeling, and they found the results that the GNPs are basically blocking the movement of the grain growth. So that is what we understood from the modeling part, that the grain growth can be restricted by these nanoparticles. With this, these are my conclusions. I think I have already told the conclusions earlier, so I'm not doing that. The good part is we have started our startup in 2019, and we have already sold some of the equipments to one lab scale DC caster. We have sold to NIST Trivandrum, and MNIT Jaipur also this nano caster. So if anybody is interested, they can contact us regarding this. And these guys have published papers with our company's name also, they have mentioned in this. So it is like, if you want to make nano aluminum composites, and these are much cheaper than what stir casting you are getting in the market. Okay, and with that I would like to end, and